Hi everyone, and this is Saran from BBC Engineering College, Vadalarevu. So today we are discussing about the Nmos Transistor circuit design. And before going to that, we have to go about and what is the introduction about Mos Transistor Model. See this is Mos Transistor Model. And coming to this, so why we are going for this Mos Transistor Model. So nowadays, so we all are using mobile phones or electronic goods, and each and every electronic device should be made with transistors. Nothing but integrated circuits. Integrated circuit is the combination of a multiple number of transistors. For the designing of these ICs, we are using different types of MOS transistor models, and those are Nmos Transistor Model, PMOS Transistor Model, and CMOS Transistor Model. These are the three different types of transistor models we are using in the designing of MOS transistor models in the process of IC fabrication. Now coming to this, here the Nmos transistor is again classified into two types, and those are enhancement mode Nmos transistor and depletion mode Nmos transistor. Similarly, the PMOS transistor is also be classified into the same two types, that is enhancement mode PMOS and depletion mode PMOS. Here the CMOS can be the combination of Nmos and PMOS. By the combination of these two, we are getting the CMOS transistor model. Now coming to the symbol representation for Nmos transistor, that is for depletion mode and enhancement mode. For Nmos transistor, the symbol should be like this. This is the gate terminal, and this is drain, and this is source. Okay, that is for depletion mode Nmos transistor. And similarly for this is depletion mode, and coming to the enhancement mode, gate, drain, and source. Simply you can observe the difference here. The thickness of the oxidation layer should be more for depletion mode transistor. Enhancement mode should be like this, and this is for Nmos transistor model. And coming to the PMOS transistor model, the depletion mode transistor and enhancement mode transistor. The depletion mode transistor should be and simply we can use one bubble indication here. That's for gate and drain and source. And similarly for enhancement mode, and this is gate, drain, and source. Okay, this is about Nmos transistor model and PMOS transistor models. Okay, and coming to the CMOS, for the CMOS should be the combination of these two. But in coming to this CMOS transistor model, we are using only Nmos and PMOS transistor in enhancement mode only. We are not using any depletion mode transistors in the CMOS case. We are using only enhancement mode transistor only. Both Nmos transistor as well as PMOS both are enhancement mode only. And now in this session we are discussing about the Nmos transistor model. Now coming to the Nmos transistor model, okay, so coming to MOS transistor model, it consists of two types of transistors. Those are so pull up and pull down transistors, any type, that should be either Nmos transistor model or PMOS transistor model or CMOS transistor model, but the functionality will be different for each and every transistor model. Now coming to this Nmos transistor model, simply the block diagram for any logic expression or any function by using Nmos transistor model should be like this. And this is so pull up transistors and pull down transistors. Here the VDD can be applied to the so pull up transistors, and this should be considered as a ground. Simply you can take it as VSS, and output is always be obtained in between pull up and pull down transistors, that is output. Okay, and coming to here, in the case of Nmos transistor model, the input should be given to only for the so pull down transistor only the input should be given to the only so pull down transistor. Okay, now so coming to the so how many pull up transistors and how many pull down transistors you can use in the process of Nmos transistor model, that should be depending on the so Boolean expression, for which Boolean expression you want to be designed the Nmos transistor model. Okay, based on that expression only you can decide so how many so pull up and pull down transistors required. Okay, now coming to the now it has to be go with so how many transistors be required for that. Now you can discuss now. In this case, the number of so pull up transistors, the number of so pull down transistors. Okay, the number of so pull up transistors required for the Nmos transistor model is always be only 1. Okay, the one must be depletion mode Nmos. So depletion mode Nmos transistor only one we can use in so pull up transistor case. So now coming to the so pull down transistors, that should be equal to the number of input variables, the number of input variables in the Boolean function, the Boolean function. Okay, and there should be enhancement mode Nmos transistors. Here the pull up transistors are depletion mode Nmos, that must be only 1, and coming to the pull down transistor should be equal to the number of input variables in the Boolean function, those are enhancement mode Nmos transistors. Okay, now so coming to here, we are having a multiple number of so pull down transistors. Now all these pull down transistors should be connected in which format? Okay, generally the transistors are connected in either series or parallel. Okay, how can you decide the transistor should be connected in series or parallel? So for that case, so I will give a simple table to remember how to connect all these transistors in any format, that should be either Nmos or PMOS or CMOS logic. Okay, so for example, if any Boolean expression should be like this, A plus B, or Z is equal to B into C, and see here in this case, and what is the operator we are using in between A and B? That is plus. So plus indicates here, that is OR operator, and coming to here there is a dot indicates here multiplication, that is for AND operator. Okay, simply we can remember these concepts, that is either addition or product logic. Okay, for this case either OR logic or AND logic, and that is for Nmos transistor logic or PMOS transistor logic. Okay, and coming to this, if PMOS transistor logic, otherwise Nmos transistor logic. If Nmos transistor logic for OR operator, that means addition. The Nmos transistors are connected in parallel, And for the same Nmos transistor logic for AND operation, all the transistors are connected in series form. Similarly, for PMOS logic, there is quite opposite function for the Nmos logic. For the PMOS transistor logic, for OR operation, the PMOS transistors are connected in series, and AND logic, the PMOS transistors are connected in parallel. Simply you can remember this table. Okay, based on this table only we can implement it any function. And one more important point in this MOS transistor logic, in any MOS transistor logic, either NMOS, PMOS or CMOS, the output should be a complement output is generated. Okay, if you want to be generate any expression like Nand gate, so Nand gate should be, so y is equal to AB whole bar. Okay, we are not able to bother about the complement, simply we can consider AB, then the finally the output should be automatically generated the whole complement. Whole complement is automatically generated here. Okay, if you want to be generate OR operation, that is equal to A plus B, but here not complement will be there. By using this MOS transistor logic, it generates A plus B whole bar. Again we has to be use one more inverter for this, then only you can get A plus B whole bar that is equal to A plus B. That is our final result. Okay, now we can discuss this concept continues. Now, so coming to the next one, now you can consider one example. Simply initially I will consider one Nmos inverter. Okay, now we can consider what is the Boolean expression for this. So y is equal to A bar. Simply you can observe here, the Boolean function consists of how many variables? Only one, that is A, and there should be a complement output A bar. Okay, that means we don't need any external inverter at the output level of the Nmos logic. Okay, now as we discussed previously, first we can list out so how many pull-up transistors are needed, how many pull-down transistors are needed. For the Nmos transistor logic, the number of pull-up transistors is equal to so many? Only one. That must be depletion mode Nmos. Now coming to the number of pull down transistors should be equal to the number of input variables in the Boolean function. Here the Boolean function having only one input variable, that is A, that should be only one, that must be enhancement mode Nmos. Okay, now so coming to the designing, see here, first you can consider the VDD, and this is ground, that is VSS. Okay, now coming to see here the pull-up transistor, it has to be placed the pull-up transistor here and pull-down transistor here. The output should be obtained in between these two. So coming to the pull-up transistor, that is depletion mode Nmos. And this is depletion mode transistor, and here for this case we can connect the gate terminal to the source. This is depletion mode transistor, that is pull up, depletion mode Nmos. And coming to the pull down transistor, pull up transistor logic is over, and coming to the pull down transistor, then is enhancement mode Nmos transistor. Okay, so as well the previously you can discuss here, the input should be given to the pull down transistor only, that is gate, drain and source, and the input should be given here, and the output should be obtained in between pull up and pull down transistor, that means here, that is y is equal to A bar. Okay, now we know that the truth table for that, input A is equal to A and y is equal to A bar. Simply can give 0 or 1. When we can give input is 0, the output should be 1, and if we can give the input is 1, the output should be 0. Okay, now we can verify our design circuit is generate the truth table or not. And before going to this operation, we must know about how the transistor should be operated. So coming to here, the Nmos transistor is operated, should be either on switch or off switch. So okay, when it is on switch, when the gate should be signal should be 1, then only the Nmos transistor is on. If it is off, when gate signal is 0. Okay, what will happen when gate signal is 1? Simply when we can give the input is 1, simply the drain and source should be both are shorted, simply acts as a closed switch, that is on state. Okay, if you give 0, okay, there is no current conduction in between drain to source, that means there is no current path between drain to source, that becomes off state. Okay, that is a switching function of a Nmos transistor. So based on this property, we can observe the operation of a inverter. Simply now we can give input is equal to 0. If you can give the input is 0, simply the transistor should be off state. Okay, if it is off means there is no current between drain to source, simply acts as a open switch. If it is open means there is no current path between VDD to VSS, that means 100% the output should, the VDD should be passes towards the output, that is Y is equal to VDD, nothing but logic 1, when we can give the input is 0. And similarly, if we can give input is 1, if it is input is 1, simply the transistor pull down transistor should be on state. If it is on means there is a possibility of current path between drain to source, simply there is a path should be exist between drain to source, then the entire VDD will be comes to in this junction, and if the transistor is on, simply it should be forwarded to VSS, that means there is no current path to the towards the output, then the output should be 0. Okay, that is the operation of a inverter. Okay, now you can consider one more example for a 2-input Nand gate. 2-input Nand gate. Simply the Boolean expression y is equal to a into b whole bar. Okay, now in this case we can discuss the number of pull-up transistors is the number of pull down transistors is. Here in any case in the Nmos transistor logic, the pull-up transistors are always be equal to 1, that is depletion mode. So here the number of pull down transistors should be equal to the number of input variables. Here we have 2 input variables A and B, then you can consider the pull down transistors are 2, those 2 are enhancement mode and Mos transistors. Okay, now it has to be designed the circuit. Thus you can consider VDD and VSS. Okay, so further, coming to the, first we can design the pull-up transistor. There should be only one, that must be a depletion mode and Mos transistor. This gate is connected to the source always, this way depletion mode and Mos for pull-up transistor. Now coming to the pull down transistor, we are having 2 transistors are here, and the logic is A, B, that indicates AND operation. For AND operation, the Nmos transistors should be connected in series. Now it has to be connected, these 2 transistors are in series. So series means if the source of the one transistor is connected to the drain of the another transistor, that is the formation of a series. So parallel means both drain of the one transistor is connected to the drain of the another one, the source of the first transistor is connected to the so source of the second transistor. There is a combination for parallel. Now coming to here, the AND operation means the NMOS transistors are connected in series. Now you can consider these two transistors. So these two transistors are enhancement mode. You can show the transistor numbering T1 and T2, and the inputs must be given here A and B. Okay, the output should be, and these two are comes under pull down transistor. The output should be obtained in between pull up and pull down, and this must be this one. Y is equal to always a complement output. Simply you can consider AB. The output should be AB whole bar. Okay, the truth table for the NAND gate is Y is equal to AB whole bar, and the combination 0 0 0 1 1 0 and 1 1. The output should be 1 1 1 0. Okay, now we can verify all these combinations. Okay, if you can give both the inputs A equal to 0 and B equal to 0, so what will happens? Simply, as we know, the NMOS transistor, when the input is 0, what will happen is simply both the transistors are in off state, because both the inputs are 0. For T1 transistor, input is 0, then it is off state, and for T2 the input is also be 0. That means both the transistors are off state. Simply acts as a open switch. That means there is no current flow towards the ground. That means the entire VDD will be flows towards the output. Then the output should be 1 when both the inputs are zeros. That is the first case. Now coming to the second case, when the inputs are 0 1. Okay, if it is 0, the first transistor T1 is open, that is off state. The second transistor is 1, that means on state. Even though the second transistor is on, because of the transistor T1 and T2 are in series. That means there is no current path in between these two nodes, because one of the transistors are in open. Okay, both are in series, then one of the transistors is open means there is no current flow. That means again the entire VDD will be flows towards the output, that is 1. And coming to the third condition, 1 0. Okay, this is as same as the previous condition, both are reverse operation. Now the T1 is on state because the input is 1. Now the transistor is on. Now in this case B is equal to 0, the second transistor should be off state. Again the entire path should be open, because of the one of the transistor is off. The path should be open. Again the entire VDD should. Hi everyone.